Hello everyone, and welcome back to another video, and today we're going to be finding the nth derivative of x e to the ax, for a being any complex number, and this is going to be featured in the next video I do as well. We're going to be using this identity, so that's kind of why I wanted to dedicate a video just to this. So yeah, we're just going to be doing this by induction, but before I do, we're just going to be writing out some of the derivatives of this, just to kind of get a feel for the general rule, and then basically prove that by induction. So, what we're starting with is x e to the ax. And I'll write this in almost like a table sort of format. So we have like our derivative number on the left, and then our actual function on the right. So the 0th derivative is just our normal function, which is just x e to the ax. So if we differentiate that once, what we're going to get, and we'll do this like 1, 2, and like maybe 3 times. So if we actually differentiate our function x e to the ax by product rule, this really isn't that bad. We just get e to the ax plus ax e to the ax. And what we can do here is just factor out this e to the ax. So what we're left with is an ax plus 1 times e to the ax. So yeah. Let's write that over here. We have an ax plus 1 e to the ax. Now let's find the second derivative, which we're just going to get by, differentiating this. I'm writing dot 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 because you get the point. We find the derivative of that, and what we get now is by product rule again. We get an a e to the ax plus ax plus 1 times a times e to the ax. And this time we can just factor out an e to the ax, but we can also factor out an a e to the ax. So what we have now is a e to the ax, and then a 1 plus ax plus 1, which is just ax plus 2, because 1 plus 1 is 2. So here, now we have a e to the ax times ax plus 2. And now, just to kind of hammer the point home, we can do this like one more time. So again, applying the derivative, what we get by product rule is just a squared e to the ax plus a e to the ax, and then times, bring down the a, and then we're left with an ax plus 2 here. Then if you factor out an a squared e to the ax, what we're left with then is just an ax plus 3. So if you kind of look at the pattern through these, let me write this down and then we can look at the pattern actually. A squared e to the ax plus 3. So what you'll kind of notice in the pattern here is that this number right here, the 3, matches the 3, and the 2 and the 2. The number that's being added to this ax is just the number of our derivative. And you'll also notice that the power of this a right here is 1 less than our derivative. So based on this, we can be very tempted to write the rule, and rightfully so actually, for the nth case, which would just be a to the n minus 1 of e to the ax times ax plus n. And that's going to be our general rule, but we should probably, actually prove it, so let's go do that. We need to do this for the base case, right, first. So we're just going to plug in 0 and see if that actually matches. So if we plug in 0 to this equation, you'll notice that we get, so say n equals 0, what we're going to get is an a to the negative 1 e to the ax times ax. But, well, those just cancel, so we're just left with x e to the ax. And yeah, that's our original function, as you can see. So the base case is satisfied. So all we have to do now to actually prove this by induction is take the derivative, so d over dx, of this right here, of a to the n minus 1 e to the ax times ax plus n, And what this should give us is this expression here, but as if we were to replace n with n plus 1. So yeah, it really isn't a bad derivative to evaluate at all. We can just put the an minus 1 on the outside, actually. And what we're left with is, by product rule, we have an a e to the ax, and then we're just adding an a e to the ax times ax plus n. And just as before, we can factor this out. And so what we're left with is an a e to the ax times a to the n minus 1, but I'm just going to group that into a to the n. So we have an a to the n e to the ax times ax plus 1. Or sorry, an plus n plus 1, excuse me. And that right there is just the exact same if we were to plug in n plus 1. So yeah, this is just a short little proof of the nth derivative of e, or this would be n plus 1, I suppose, of e to the ax, and then times x. So yeah, just a little induction proof for you there. Thank you all for watching, and I'll see you in the next one.